Great to see you, and thank you for coming out. And I'm honored to be the 115th chair of RCI, and we're here to celebrate, obviously, an award that we're very proud of. I think you all know, how many people are members of RCI? I recognize the number. Anybody not a member? Oh, one or two, okay, so all right. Those of you not members, please find out more about us. Our mission is simple. We're focused on providing a platform for leading Canadian and international scientists to have communications to Canadians about science. And this is what we've been doing for 168 years, and it's what we plan to do for the next 168 years in both languages. So thank you very much as well for our attempts to sing a bit of French tonight. That was great. So we've always started with lectures in Toronto. A few years ago, we expanded to Mississauga. Last night, as I think some of you know, we expanded to Ottawa. We had our first event in Ottawa in association with the University of Ottawa. And Canada's first chief science advisor was our keynote there. She introduced the panel. And so we are having great discussions with her, and we look forward to working with her more closely as we go in the future. We all are aware of and those of you who come to the science lectures at RCI, you're familiar with the science that we are doing here in Canada, and it's exceptional. It's world class, and we all know that, and the chance that we have every now and then to bring some of our leading scientists and emerging scientists to discuss this with you I think is really important. But I think there's a really interesting question about how our general public responds to science and how aware they are of it, how they react to it. And that's really what we're really interested in. Last year at the Canadian Science Policy Conference in Ottawa, we facilitated a panel on a science culture in Canada, and do we have it, and if so, what is it, and what it would look like, and how do we measure it going forward? So it's something that I think is very interesting. Tonight we're going to be talking about science and communications in particular, and I think it's an interesting question because we are in English Canada. We are familiar with some great programming that's available and media. I think a lot of us listen to Quirks and Quarks, The Nature of Things, Our Daily Planet, and last year's winner, Ivan Semenuk, who writes for the Globe and Mail. But it really is not enough, and I think we've got an example here tonight that I hope we can follow, and that is in Quebec, because our honoree tonight exemplifies what we would like to see of more throughout Canada. He's moderated and run 3 television programs to his name. Has had a number of books and a long career at the Montreal Planetarium, which, unlike our planetarium, was doing well and continues to do well. So we see evidence of support for science out there, and it's interesting. I was just, some of you may have looked at the federal budget. We were, I think, warned, all of us, that this would not be a big spend budget. That'll be next year before the election. So this was a sort of interesting one. It's, they're trying to do a little bit, but save the big money for a little bit later. And there were 12 items. The Globe and Mail focused on 12 key issues. Interesting enough, science was there. It was number 8 out of 12, so it wasn't first, but it wasn't 12th. And as you may have heard, there's $3.8 billion of new money going to science over the next 5 years. Of that, about 500 million of it will go to discovery science over the next 5 years, which is good. It's not the $1.5 billion that the Naylor panel was calling for. So it's a start. We can hope to see more progress on it maybe in the next year when it's more of a spend budget. But tonight we're very pleased to have Dr. Pierre Chastenay who's made a major contribution to this. And I think those of you in Toronto probably don't know as much about him. You're going to find out a lot more about him tonight. The Fleming Award began in 1982, and I think you've been seeing on the screen here some of the past award winners. The first winner was David Suzuki, and we've had from there many very famous people who have done this. Instead of just giving out the medal, we like to have it as part of a ceremony tonight. So we're having we're going to have a presentation, and I'd like to call on Jacque Fleming, who's relative, two greats, grandson of Sir Fanford Fleming, come up and say a few words. He's on our board of trustees and our council, and we're delighted to have Jacque. So say a few words.
Thanks, Peter. Great opportunity to be here. Yeah, my great-great-grandfather was really quite a guy. He arrived in Peterborough, June of 1845, at the age of 18. He then starts the Canadian Institute in June 1849 with some of his close friends. The Canadian Institute receives its royal charter in 1851 from Queen Victoria. The articles outlined the purpose of the Institute to have formed themselves into a society for the engagement and general advancement of the physical sciences, the arts, and manufactures in this part of our dominion, and are connected with the professions of surveying, engineering, and architecture. And although and it goes on for about 4 more pages. But it's interesting that our mission really hasn't changed. I mean, the articles have changed a little bit, and we're more focused on science and the arts, but that mission of engagement and general advancement of science is what the RCI is all about. I'll read a little passage from his diary. So this is January 1853, so he's just about 26 years old. Saturday, January 1st. New Year's Day brings to our memory, in the middle of business and certain life, that another milestone of the journey of life is just passing by, and that we are another year near the terminus of this uncertain and to all of us untraveled road. We cannot help seeing that we pilgrim are happiest in making others happy, and that we do not live for ourselves only, but that each of us have our allotted duty to perform to our community in which we live and to our fellow pilgrims. I do not regret the time I've spent, in brackets, although I deeply regret many other things, and the zeal shown in bringing into existence and into active operation the Canadian Institute, because I believe it is calculated to do great good for my adopted country, and to begin the new year well, have now resolved to provide it with an endowment of £1,000 when all that is mortal in me returns to its mother dust, the interest of which to be annually expended in furthering the objectives of the society. To effect this objective, I've already taken steps to assure my life for that sum. And actually, a few days later, on January 19th, he walks down to newly formed the Canadian Life Insurance Company and purchases an insurance policy. So interesting history when you go back in terms of his strong belief in Canada, but also the strong belief in what the Canadian Institute, the Royal Canadian Institute for Science, can empower and engage people in all walks of life. So at this point, I'd like to ask Dr. John Percy to come forward. Thank you very much.
Well, thank you very much. I've been asked to explain why I nominated Dr. Chastenay for this award, and I should start by pointing out that why I nominate anybody for any award, because this is actually one of the most satisfying things that I can do as an academic, as a scientist, and an educator, is to make sure that those, particularly in this age of overpaid celebrities, that people who do make a meaningful contribution to our society, such as by increasing scientific literacy, are made known and honored in a way such as this. Well, as we've just heard, the Royal Canadian Institute for Science has an illustrious history stretching back to 1849. And in the century following, if you've read the RCIS history, the Institute and its members, though based in Toronto, had an impact on science across the country, publishing the research of Canadian scientists, for instance, laying the groundwork for institutions such as the Royal Ontario Museum, the Ontario Research Foundation, Ontario's Provincial Park System, and the National Research Council of Canada. And the role of Sir Sandford Fleming and the Royal Canadian Institute for Science in successfully promoting international standard time should be known by every Canadian, though not necessarily it is known by every Canadian. But in the last half century, it seemed to me that the RCIS has become more Toronto-centric, though in recent years, as you've heard, it's begun to seek a national role, something that I would encourage because Canada lacks a national organization for the promotion and advancement of science, something like the AAAS in the United States. One RCIS activity which is or should be national is the Sandford Fleming Medal for outstanding contributions to Canadians' understanding and appreciation of science. Past recipients have come from across Canada, but I notice in recent years there's definitely a Toronto-centric trend, also an astrocentric trend, if you count both astronomers and astronauts, though all of those recipients have made contributions above and beyond those in their own science. So why nominate Pierre Chastenay? Well, last year, as you know, well, actually 2017, for which this medal is being awarded, was Canada's sesquicentennial. So in deciding to make a nomination, I thought it especially important to take a national perspective, to also recognize that Canada has 2 official languages. And prior to 2017, there had only been one Francophone recipient of the Sandford Fleming Medal, and that was Fernand Seguin in 1988. And a decade earlier, he'd received the prestigious UNESCO Kalinga Prize for popularization of science and had been appointed an officer of the Order of Canada. So he was obviously well-deserving. So once again in 2017, we have a distinguished Francophone science communicator, Pierre Chastenay, as recipient of the Sandford Fleming Medal. I should point out, though, that even though I'm definitely not Francophone, I was well aware of Pierre's many and diverse science communication accomplishments that transcend language. Now, last year, he was also the recipient of the Canadian Astronomical Society's KELAC Award for excellence in communicating astronomy to the Canadian public. So incidentally, let me explain KELAC, Q-I-L-A-K. So when Canadian astronomers were establishing this award, they looked around, as usual, for a name that would be meaningful in both official languages, but failed to find one, until someone brilliantly suggested, well, why don't we use a term from an Aboriginal language? And indeed, KELAC is the Inuit word for the sky or the firmament. So it reminds us Canada actually has more than 2 official languages, or at least languages. So yes, Pierre is an astronomer, but he would more than qualify for the Sandford Fleming Medal on the basis of the hundreds of award-winning general TV programs that he has hosted, notably Telescience, Le Code Chastenay, and for the many other contributions that he has made to science communication in general, and a whole page of awards on his resume. So let me now read the official citation. The 2017 Fleming Medal and Citation is awarded to Dr. Pierre Chastenay, professor in the Department of Didactics at Université de Québec à Montréal. The award recognizes Dr. Chastenay's outstanding contributions to the public understanding of science in Canada, in particular in recognition of his years of dedication in bringing science, particularly astronomy, to the public. Dr. Chastenay's career has taken him from live presentations at the Planetarium de Montréal to television with Telescience, Le Code Chastenay, and Electrons Libres. He has written award-winning books and countless articles. Perhaps most importantly, he works tirelessly and efficiently to ensure that science is taught well in schools. Together, these accomplishments form an impressive list of achievements. Through the impact of Dr. Chastenay's work, though the impact of Dr. Chastenay's work is greatest in Quebec and the Francophone world, through his publications, presentations, and his work in professional institutions and organizations, he is well known and respected elsewhere in North America and beyond. With this award, the Royal Canadian Institute for Science also recognizes the strong commitment to science outreach and to the public understanding of science in Quebec, an area in which Pierre's work has shone and gone on to make a significant impact on science communication in the rest of Canada. And we're now going to have someone else who reads the citation in French. That says something about my French ability.
No personal comments here, just the citation to keep things rolling. C'est avec plaisir que je présente au nom de l'Institut royal des sciences du Canada la médaille et citation Fleming 2017 à Dr. Pierre Chastenay, qui est professeur à l'Université de Québec à Montréal dans le département de didactique. Le prix reconnaît les contributions exceptionnelles de Dr. Chastenay à la compréhension publique de la science au Canada, en particulier ses nombreuses années de dévouement à faire connaître la science, en particulier l'astronomie au public. La carrière de Dr. Chastenay inclut des présentations au Planétarium de Montréal et plusieurs émissions de télévision qui ont gagné plusieurs prix et accolades. Télésciences, le Code Chastenay et Électrons libres. Il a écrit plusieurs livres qui ont aussi gagné plusieurs prix et un volume prestigieux d'articles qui a amené la science au public. Peut-être le plus important, il travaille efficacement et sans relâche pour assurer que les sciences sont bien enseignées dans les écoles. Tant que l'impact des efforts de Dr. Chastenay ont eu le plus grand effet au Québec et dans le monde francophone, ses publications, ses présentations et son travail dans les institutions et organismes professionnels le font connaître et respecter en toute l'Amérique du Nord et ailleurs. Avec ce prix, l'Institut royal des sciences du Canada reconnaît également le fort engagement envers la sensibilisation scientifique et la compréhension publique des sciences au Québec, un domaine dans lequel le travail de Pierre a rayonné et a eu un impact important sur la communication scientifique dans le reste du Canada. Merci.
Where's the 1,000 pounds?
It's well invested.
Any other pictures? Wow, this is amazing. Thank you very much, John. Merci beaucoup pour cette présentation. Just in case it falls. It's safer there. Let me just open this up before I begin. Do we have the image on the screen? All right, we do. Well, first of all, thank you very much for coming tonight. I know that you don't know me. Hopefully, by the end of this talk, you'll know a little more about me and a little more about the work that I do back home. I just want to say first about John Percy. There's something you might not know about John is that every year as a member of the Canadian Astronomical Society, we are supposed to report every education and public outreach that we do in our daily lives. And we take all these numbers coming from all places in Canada and we compile them. And every year for several years now, half of CASCA's education and public outreach are done by John Percy. So in the CASCA EPO committee that I sit on, we call him the wrecking machine of education and public outreach. So congratulations again, John. I think you deserve, a good hand. And I also thank you, John, because you're the reason behind this prize. You're the reason behind the KILAC prize that I got last year. Interestingly, the prizes that I win don't come with money. They come with an obligation to give a talk in English. So next time, try to find something that has money attached to it, please. So it's a great honor to be here tonight and a great honor to be able to address you. I just want to tell you how I found out about me receiving this prize. I actually got a letter from Mr. Love that was in October of 2017, stating basically that I was the 2017 recipient of the Sanford Fleming Medal, which was great. But the first question I asked myself was, what exactly is the Royal Canadian Institute for Science? And I must confess that I didn't know a lot about the RCIS. At some point, I think I confused it with the Royal Society, but you know, now I know better because I did what all scientists do when they're faced with a mystery. I Googled it. And after I Googled it, I went to the RCIS webpage, and boy, was I blown away. Well, first of all, looking at the history of RCIS, I mean, you're old, but you look good. I mean, institutions that are here more than 100 years in Canada, that tells a lot. So, and it's so important to have institutions that have all this background and history because they know where they come from and they have a better idea of where to go. So that's very, very good. I also, of course, discovered, but I had a clue because it was the Sanford Fleming Medal. I discovered that the RCIS was founded by Sanford Fleming. And that resonates with me a lot because Sanford Fleming was a land surveyor, and so was my father. So there was a connection right there. I used to say that my father was a surveyor of the land, and I became a surveyor of the skies because I became an astronomer. But I guess he would have been proud for me to receive this prize tonight. After that, I went to the Sanford Fleming recipient page, and I was blown away again. Of course, you've seen the names of past recipients. Paul Delaney, who's in the room, is a past recipient. John Percy as well. But there's one name, and John mentioned it in his presentation. There's one name that, again, resonates with me a lot. It's Fernand Seguin. Because when I was a young kid, Fernand Seguin was on TV, he was on radio, he was talking about science, and he's one of the few people who got me interested in science, along with Carl Sagan, with the Cosmos television series that I binge-watched even before binge-watching was invented. People like David Suzuki, of course, had a huge influence on me. And so it's just amazing to be on that same list with all these luminaries, all these people who done so much for science education and science popularization in Canada. My education and public outreach career began when I was 11, and I'm not kidding. The year was 1973. John, you probably remember Comet Kohoutek. It was supposed to be the comet of the century. And I was so excited. I was into astronomy for some years now at that stage. I was 11, I was in grade 5, but I was very, very much interested in astronomy and science. And I was so passionate about it, and I was so interested in that comet in particular that I decided to convince my 5th grade teacher to let me do a show and tell. It's not often that kids go to their teachers to do a show and tell. It's usually the reverse that happens. And she accepted, and so somewhere in the fall of 1973, I was talking to the classroom, showing them, you know, drawings on the board. I had made photocopies of the trajectory of the comet to make sure that they were able to see it. I was really, really into it. Unfortunately, predicting comet brightness is notoriously tricky, and it turned out that Comet Kohoutek was a dud. I couldn't even see it myself. But the feeling that I got from, you know, speaking to the class, sharing my knowledge, my crude knowledge of comets, and the passion that I had for astronomy, that stayed with me. And I think that 11 years old, 1973, that's where my career started. That's where I became a popular, or a science popularizer, if you will. I worked with my father on land surveying for several summers when I was a young teenager, but my real first job that I, you know, landed myself because I was in the interview and I got the job, it was at the Observatoire du Cégep de Trois-Rivières. I was 17 years old. I was just finishing high school, moving on to college, which is in Quebec, just before you go to university. And I was hired for 2 summers, and I was basically having groups by the end of the day, and we were showing them slides, actual physical slides, not the one that you see now that are virtual and electronic. And when it got dark, we would climb upstairs to the dome, and I would be surrounded with the astronomical instruments, the telescope. We had a huge Celestron 8-inch that was state-of-the-art back then. And we were using, I was with other colleagues, and we were using this to, show the moon, the planets, the Andromeda galaxy by the end of the summer. It was amazing to be able to share that excitement and be able to show the people the wonders of the sky. And again, that's where I discovered that I could be an astronomer. I could earn a living by doing what I liked, which was studying astronomy and sharing my passion with people around me. So I moved on to university. I did a bachelor in physics, a master's in radio astronomy under Serge Pinault at Université Laval in Quebec City. And then I moved to Montreal, and I started to study a PhD in galactic astronomy. And I was basically looking at, photographic plates all day, trying to find small galaxies that were specks of light. And I remember asking myself, is that what you want to do for the rest of your life? And I decided that no, what I wanted to do is study astronomy, but be able to share the excitement and the knowledge and the passion that I had for this science. So I decided to leave the PhD, and I was lucky enough to find a job at the Montreal Planetarium, which was back then called the Dow Planetarium. And I guess that most of you who've been in Montreal have visited the Dow Planetarium. It's now closed. There's a new facility that you absolutely have to go to. I'll discuss that in just a few moments. But I spent 25 years at the planetarium. I was producing shows. I was producing exhibits. I was writing weekly columns in newspapers. I was doing TV and radio interviews. It's been a wonderful 25 years. And I was lucky enough to be part of the team that designed and built the new Montreal Planetarium, which is called the Planetarium Rio Tinto Alcan. That again, I urge you to visit the next time you're in Montreal. It's a state-of-the-art facility, and I just hope that someday Toronto has a better planetarium than this one. I mean, Toronto is a world-class city. It deserves a planetarium, so go ahead and get it. So that's been 25 years of my life, working as a science popularizer, a science educator in the planetarium. But, in parallel with that, I also had a career in TV and media. John mentioned it. I've been the host of Le Code Chastenay for 8 years. It's a show that earned awards from the Academy of Television in Canada. For 2 years now, I've been the host of Electron Libre, and that's another way of doing science education. You're not, you're not having people trapped in the planetarium for 35 or 40 minutes that you can talk to. You're basically throwing bottles in the water, and you hope that those bottles of knowledge and interest will get grabbed by people, and that they will be interested in science. It seems to be working. I mean, we have a huge following on TV, huge in terms of state TV in Quebec, because this is basically like TV Ontario, but only smaller. But it's been doing great, and I just love doing that kind of stuff because, again, you reach so many people at once. It's mind-boggling. So I was working at the planetarium. I was also doing these TV hosting on Télé-Québec. And for the last 10 years, I was also back in school because I wanted to understand what was working and what was not working when I was producing planetarium shows or mounting exhibit or writing text that people would understand or not. And so I decided to go back and do a master's in science education at Université de Montréal. And as often happens, my master's project got bigger and bigger and bigger, and it became basically a PhD project. And the nice thing about that, it took me 10 years to complete it. So, I mean, if you're in that, be patient, it'll come. Took me 10 years to complete my PhD, and the day after I completed my PhD, which was 4 weeks after we opened the new planetarium, Université du Québec à Montréal gave me a call, and they told me, well, if you're interested, we have a professorship for you in science education. It didn't take a long time to convince me that this was the dream job that I was hoping for. And so now, for almost 6 years, I'm no longer working at the planetarium. I'm still hosting the TV show, but I'm now a professor of science education at Université du Québec à Montréal, and I'm basically teaching future primary teachers how to teach science. That's the stuff that I do. I think it's important because the multiplicative effect of that is huge. I have 50 students in every class. I have 2 classes per semester, so that's 200 students every year that I meet. And I try to convey to them the importance of teaching science at the primary level and, ways of doing that will be interesting for the kids and that will help them discover what is doing science exactly. So that's what I do in my teaching. But what I want to talk to you about for the next 2.5 or 3 hours, of course I'm kidding. I mean, I'm giving a speech in English, which is not my first language, so the shorter the better, believe me. But what I want to talk to you about for the rest of my presentation is the research that I'm doing, because yes, I'm teaching, I'm hosting a TV show, but I'm also doing research in astronomy teaching. And this is what I want to discuss for the rest of the presentation. So the first thing that I did when I became faculty was to launch a survey, because I wanted to know how primary school teachers teach astronomy in their classrooms. And this information was not available. There were no surveys that had been made already on that subject. So I made a first survey one-on-one in person with 138 primary school teachers, and then I did another one online with 500 respondents. And what I discovered is that less than half of the primary teachers that I interviewed teach astronomy to their classrooms, which means that there's one kid in 2 or one classroom in 2 that doesn't hear about astronomy at all during the primary school level from kindergarten to grade 6. And what I discovered as well is that most primary teachers teach science less than 1 hour per week, which is not much, you must admit. And for those less than half of the respondents that I interviewed that do teach astronomy, what I call the astronomy teachers, they do astronomy between 6 and 10 hours every year, which is not much either, if you consider it. Now, why is that like that? Why is that situation happening? Well, I think part of the reason is that when you look at the background of these people, primary school teachers, and you look at, for instance, the highest level of school, of education with courses completed in physics and chemistry or in biology, you see that for most of them, it was in high school, which means that when they get to teach in their classroom after 2 years of cégep and 4 years of university, it's been 6 or 7 years since they've done science. So for them, science is not present, it's not important. It's something that they did. They probably didn't like that much, because otherwise they would have been, studying science and cégep at university. So there's a problem right there. The second thing I discovered by asking questions is the level of satisfaction with their pre-service training in astronomy and science and in science teaching. And you see that for most of them, it was not satisfying. They were unsatisfied or very unsatisfied. But what's most worrying is the last column or the last 3 columns, where you see that for most of them, there was no training at all in astronomy when they were studying to become teachers. So it's not surprising that they don't teach astronomy, since they got no training in astronomy. So that's a situation that I'm working on, trying to bring up more astronomy education in the formation of future primary teachers. And the last thing that I think is talking a lot is the fact that when you ask about the perceived effectiveness of in-service training in astronomy, so when they're actually teachers and they go to professional development days or things like that, well, for most of them, astronomy does not exist. They got trained in French, in English, in math, whatever, but there's no training for in-service teachers in astronomy. So that's the situation that I discovered, and I'm pretty sure that if I did the same survey in Ontario or Manitoba or somewhere else in the United States or Canada, I would get basically the same results. Another question that I asked those in-service primary teachers is, what do you use to teach astronomy? That's for the about 250 of my primary teachers who do teach astronomy. What do you use? What are the tools that you use to teach astronomy? And it turns out that for most of them, it is the textbooks and the exercise books. So for most of the kids who do hear about astronomy in the primary classroom, they hear about astronomy by reading and writing about it. They don't hear about astronomy by looking at the sky using a star wheel or a star finder or telescope binoculars, a sundial. It does not exist. Teachers don't know how to use it, so they won't teach it. So because textbooks are so predominant in teaching primary school astronomy, I wanted to know what's in the textbooks. So what do the textbooks tells the kids, you know, in terms of astronomy? So, and this is a research that I started about 2 years ago. It's ongoing, it's not published yet. But I'll just show you 3 images to illustrate what I'm talking about. So look at this image. And this is a classical illustration of the solar system that you'll find in any primary school textbooks. Can you tell me what's wrong with an image like that? You have any clue? It's out of scale. I mean, planets are too large, they're too close together. Look at the asteroid belt. I mean, it looks like a gravel pathway. So when you show an image like that to a kid who's 9 or 10 or 12 years old, the image he or she builds in his or her mind is an image of the solar system that has nothing to do with the real thing. And you know, there even one kid, because another thing that I did was sit down with kids with those textbooks and ask them to explain what they understood from the images that were in the textbooks. And one of the kids told me, well, I think the planets, they move around the sun, but they follow a track, like a train. Because on all of these images, you have the orbits that are drawn, and for the kids, this orbit must be something physical. So, you know, it's like a train moving on a track. That's the kind of mental images that the kids build by being in contact with images like that. That's another classic example. This is a diagram that is supposed to explain the phases of the moon. Now, if you're an astronomer like John or Paul or me, I mean, you can easily get a sense of what it means. But for a 9-year-old, I'm not sure. And for most kids, what they'll get out of this image is that, first of all, the orbit of the moon around the Earth is a very flattened ellipse, whereas the real orbit is almost circular. Most of the kids will believe that there are many moons at once around the Earth, and that because the Earth rotates on its axis, we face each of these phases from day to day, hence the phases of the moon. I mean, and you are supposed to figure out with this image that all the images of the moon on the outer circle are actually what one would see from the surface of the Earth if we were looking at each of these moons. There is no legend, there is no text helping the kids reading this page to make sense of what he or she sees. So, you know, it goes in all directions. One last example, another classic illustration to show the seasons. Now, by now, you begin to look at these images with another eye. And when you look at this image with the eye of a child, what you see is that the distance between the Earth and the sun varies a lot. And it makes great sense to a 9-year-old that when the Earth is farther away from the sun, it gets colder. And when we're closer, it gets warmer. Hence, the misconception about the seasons that it is due to the varying distance between the sun and the Earth. Whereas the real variation is 3%. It's insignificant, and moreover, we are closer to the sun on January 4th than on July 4th. You couldn't tell that by being in Toronto in the wind on January 4th, but it's true. So, all the data that I've just presented you, this is the situation that I'm dealing with, trying to teach astronomy and make my students teach astronomy better than using the textbooks. So that got me thinking about how could I teach astronomy better in the classroom and in a primary classroom. And that got me thinking further, asking how do astronomers do astronomy? And is there a way that I can take the way astronomers do astronomy and translate that and transfer that to the primary classroom? That got me thinking even more. How do astronomers do astronomy? Well, it all starts with a question. There's no science if there's no question. If you don't ask yourself questions and you discover things, you don't do science, you do chance, basically. So it starts with a question, but astronomy is a particular science. I dare to say it's a distinct science, although it might not be the right word to use. But astronomy is different because there is no way you can do experiments in astronomy. You cannot take a star or a galaxy, bring it in the lab, cut it in half and see how it's made inside. The only way you can learn anything about astronomy is by looking. It's by observation. That's why we build telescopes. That's why we build detectors that can look at the infrared and the ultraviolet and the gamma rays, and we have telescopes and satellites in the sky to look at all the electromagnetic spectrum. Because that's the only way we can make sense of the world. But only having observation is not enough. What astronomers do when they have all these observations is that they try to model it. They try to create a model. It could be a physical model, it could be a mathematical equation, it could be a computer program, whatever type it takes. But they will basically create a model that will first have to reproduce the observations. That's the first step. And the second step of the model will have to be able to make predictions that will then lead to more questions and more observation. And you see now how the cycle of astronomical discovery works. Let me give you just one classic example. There would be many, but just one example. This is the end of the 16th century. We are still living in a world where the Earth is at the center of the universe. But more and more people who make observations with instruments to measure angles and things like that, they find that the results of their observation is at odds with the predictions based on the model of Ptolemy, which places the Earth at the center of the solar system and which makes all the other objects revolve on circular orbits around the Earth. So there's a difference between the predictions and the observations. So clearly something is wrong. But what exactly is wrong? Well, the only way to find out is to make more observations, and that's what Tycho Brahe will set out to do between 1582 and 1600. He will observe the planet Mars with the most precise instruments of his time, and he will gather observations after observations of the planet Mars because he wants to understand how it moves in the sky, what's responsible for its movement in the sky. The guy was rich. He was able to build his own observatory on an island that he owned somewhere in Scandinavia. I mean, astronomers don't have that kind of money these days. If you plot the observations made by Tycho Brahe in a more modern form, this is what you'd get. Of course, there are blank spots. There are places where data is missing because obviously sometimes Mars is behind the sun and we can't see it. But you can tell already that there's a cycle there. There is something repeating in that data. And it's the role of the model to be able to explain exactly why the data has the shape it has. And it's not Tycho Brahe who did that work. Actually, Tycho Brahe died and he gave all his observations to Johannes Kepler, who was his assistant, and he was a bright mathematician. And what Kepler did over the years after Tycho Brahe's death, he tried to find a way to calculate and reproduce the observations that I've just shown you. And he had two hurdles to overcome. First, he had to move the center of the solar system from the Earth to the Sun. That was relatively easy to do because he was kind of convinced that Copernicus was right and that the Sun was at the center of the solar system. The second hurdle he had to overcome was the idea that the orbits of the planets were circular, were circles, because that idea dated back to the Greek philosopher and it was hard to let go. But at the very moment that Kepler tried other conic sections than the circle, and he tried the ellipse to represent the orbit of the planet Mars, eureka. His model worked. Not only his model worked in reproducing the observations that were gathered by Tycho Brahe over the 20 years before, but he was able to use his model to make precise calculations of the future position of the planets. He published the Rudolphine tables in 1627. And these tables were the most precise ever calculated and ever published. And they were so precise that with these observations and with these predictions, people were able to predict the transit of Mercury of 1631 and the transit of Venus of 1639. So it was quite an accomplishment. And of course, because we had a model that worked, we were able to ask new questions and make new observations and, refine the model. That's how science works, and that's how astronomy in particular works. So I come back to the idea of how to teach science to primary school kids. Could this model, this approach that I've just shown you, work in the classroom? Well, let's give it a try. And that's basically what I've been doing for the last 3 to 4 years. The idea is, for instance, to teach the phases of the moon to children in grade 5 and 6. So it begins with a question, of course. It begins with the question, how come the moon changes shape over the course of 1 month? And how do we go about trying to find an answer to that question? Well, we observe the moon for 1 month. It's been done before. I mean, I didn't invent that, but I certainly cast it in a certain theoretical framework. And so the kids have to observe the moon for 1 month. And after that, we look at the data that they've gathered, and we try to come out with all the information we need to create a working model that will help not only explain the observations that we've made, how come the phase of the moon happens, but we'll also be able to predict new phenomena that maybe the kids didn't know were related to the phases of the moon. One of which is, of course, eclipses. And the other one is the fact that if there are phases of the moon as seen from Earth, then there are phases of the Earth as seen from the moon. It's exactly the same mechanism. There are phases of Mercury and Venus if you look at them from the Earth. So, of course, in grade 5 and 6, children are too young to reinvent everything by themselves, and that's not what we want them to do. So they need scaffolding, and this scaffolding may come in the form of a table like that they have to fill. So the goal of the children, the students, is to fill 1 line every day. So they have to find out at what time and at what date the moon rises, the moon sets. It's shocking for most of them to find out that sometimes the moon rises on a Friday and it sets on a Saturday. I mean, they didn't see that coming at all. It's also shocking for most of them to find out that you can see the moon in the daytime. They didn't realize before. But now they have to, because they have to be very specific about the observations that they made. I asked them, of course, to draw the aspect of the moon, the phase, to name the phase if they can, and also to measure the percentage of illumination of the moon and the elongation of the moon, which is the angle between the moon and the sun as measured from the surface of the Earth. Now, they do that they're thorough in their investigation. They want to find an answer, and they're convinced that this is important because, they were told that it's something that they had to do. And once you have 4 weeks of observations like that, you can begin to do very, very interesting science with primary school kids. One thing you can do is, for instance, plot the illumination of the moon relative to its phase. And what you find is that the illumination being basically the fraction of the disk of the moon that is illuminated by the sun, as seen from Earth. And you can see that at new moon, obviously, the illumination is 0. But when you get to full moon, it's 100%. So it rises from new moon to full moon, and then it decreases from full moon to the next new moon. There are 2 cycles, two cycles of phases in this diagram. This is something that the kids have to do. I mean, they have to find a way to represent, and it's very important that they learn that in science, it is sometimes by drawing graphs that you find the information that you're looking for. Another very interesting graph is the allegation of the moon relative to its phase. Again, this measures the angle between the sun and moon as the cycle progresses. It is close to 0 at new moon, but it's not exactly 0, because otherwise it'll be a solar eclipse. And when you get to full moon, it's not exactly 180 degrees, because again, if it would be exactly 180 degrees, it would be a lunar eclipse. So this is something that you can begin to work out with the kids. Another thing that they can do, only based on their observation, there's no teaching here. It's only the kids making sense of the observations and the note they took, is to ask them to fill this table. So for instance, they have to find out, but it's in their observations that on the first quarter moon, the moon is 90 degrees from the sun. It's in there. It's in the table. The moon rises around noon. It sets around midnight, and it's visible all afternoon and all evening. Again, no teaching. Only get your data and use your data to fill the table, and it works. What I did with this idea is basically train teachers during in-service teachers training that was 2 days, 1 month apart. And basically, I asked the teachers to do exactly what I've just described. Observe the moon every day, use stellarium, you all have these days telephones, right? iPhones and Google phones and things like that. And you can have astronomical applications that will give you all the information you need to fill the table without looking at the moon. Because obviously this is Canada in the winter, and we see the moon maybe once or twice a month. But the information is available, it's there, and it's easy to find to fill the table that I've just shown you. So I had 18 primary school teachers following this trend and participating in this training. And during the second day, we spent the whole morning looking at the data that they've gathered and trying to figure out how to graph the results and try to come out with sentences that would describe what the moon does during a whole cycle. And it was very clear in their head what they had to model. So the afternoon was basically, here are styrofoam balls and flashlights, and we were in the darkened room, and go crazy, but try to find a solution to the problem. Try to find a way to model what you just observed. And it didn't take very long for them to figure out that, if you hold a styrofoam ball at arm's length and you have a flashlight shining on the styrofoam ball and you turn to your left, you reproduce exactly what was observed during 4 weeks. But now you want to make it interesting. So what if someone holds the ball? You're the Earth, and you have to make round rotation every day while the moon moves about 15 degrees on its orbit. Then you can model the way the moon rises and sets later and later every day. Again, using, styrofoam balls and flashlights and things like that. And you can ask even more interesting questions like, okay, what about looking at Venus or Mercury, which are orbiting inside the Earth's orbit? Could we see phases? Of course we could. And it's easy to understand. Once you figure out how phases of the moon occur, it's easy to figure out how phases of Venus or Mercury occur, because they are solid spheres. They are lit by the sun. So there's one hemisphere that is bright and one hemisphere that is dark, because it's in Venus's or Mercury's self-shadow. And because the angle between the sun, the Earth, and Mercury or Venus is changing, then the fraction of the lit hemisphere that we see from Earth changes as well, hence the phases. It's exactly the same phenomenon. And you can ask even more interesting question, and I think that's the best question to ask. Could we see phases of the Earth if we were on the moon? Well, the answer is yes, of course. And this is a picture that was taken on December 12, 1972. Gene Cernan, who's the American astronaut holding the camera, is taking a picture of Harrison Schmitt holding the flag. This is Apollo 17. That's the last landing mission of the Apollo series. And you can see in the background, there's a phase of the Earth. It's a gibbous Earth, so to speak. The interesting thing we can do these days is use planetary software like Stellarium to find out what was the phase of the moon on the same day. You just enter December 12, 1972, enter, et voila, you have the answer. And this is the answer. So this is the phase of the moon as seen from Earth at the same time that the astronauts were taking a picture of the Earth. And what's interesting, and this is something that actually a teacher told me, because I didn't notice before, is that the phases of the Earth and the phase of the moon are reversed. They're complementary. So if it's full moon and you're on the face of the moon, you see new Earth. If it's new moon and you're on the face of the moon and you look at the Earth, it's full Earth. First quarter moon, last quarter Earth, etc., etc. And this is something that was realized by a primary school teacher after, working with these models and looking at these observations. Obviously, I'm a scientist, and the idea here is to make measurements, trying to see what works, what doesn't. So this project that I just described to you, it's a research project. I actually use a questionnaire about the phases of the moon to find out before and after a lesson what was gained, what was understood that was not understood before. I also use a questionnaire about self-concept. This is extremely important for primary school teachers to feel competent enough to teach astronomy, and self-concept measures, the level of confidence that you have when you discuss about a subject. I mean, I'm pretty self-confident right now talking to you about that. I wouldn't be so self-confident if I had to give a speech about Canadian politics or economics. I mean, that's the kind of thing that you can measure with these questionnaires. And I'll complete my presentation with 2 slides that show you the results that I got with the 18 teachers who were trained for a month looking at the moon and then modeling the moon. You can see that the difference between before and after the training for self-concept and phases of the moon is significant, and there's an effect size which is interesting. And I was fortunate enough that 2 of these teachers decided to do the same thing with their students, 5th and 6th grade. And I was able to make the same measurements with pre-test and post-test with the kids. So you see the result, the table 3 is the result for the self-concept. So you see that the difference between before the lesson and after the lesson is highly significant. The effect size is huge. It's almost too good to be true, really. Same thing with the same measurements that I did 2 months after the lesson. So the information, the self-concept, their feeling of being competent enough to understand the phases of the moon, it hadn't changed. For the phases of the moon, I also have a huge difference between before and after, with a huge side effect. You see 2 months after a small decline in their understanding of the phases of the moon, which is normal because, these things need time to really get into you. But still, even after 2 months, the difference between after and before was still significant and with a large effect size. So that's the kind of thing that I do to teach astronomy. Just to open up on the question of teaching science and educating the public into science, I think that this example shows that when you are trying to teach a subject and you genuinely try to do it the way that the scientists work, not by showing only results, but by showing how science is done. I think the lesson here is that it'll get people more interested in science because, science is a human endeavor. And it's important not only to know the results, but also to know all the travails and all the problems that the scientists had to get to these results. And so that the kids or, the parents or the public that we are addressing has a real idea of how science is made. Not only its results, but the way it is pursued and how we get to these results. Again, I want to thank you very much for being here tonight. I hope that I did not bother you too much, and have a nice evening. Thank you.
Very good. Very good. I think we're going to...
I think I go and sit, right?
You could go sit. Yeah. For the Q&A. I think Pierre's going to be around for a few minutes. Anybody have a question they want to ask at this point? Because we're invite you back out there. I was saying to Pierre before, it was interesting on CBC earlier this week, last week, there was a program and an analysis of the number of Chinese students in not just universities in Ontario, but actually high schools. A lot of Chinese people are sending their kids here to Toronto to be in high school. Part of it is so they can get into good Ontario universities. But the other part was, and they interviewed a number of the parents, and they felt that too much of the teaching in China, and especially in the sciences, was by rote. It's just memory work. Just memorize the sky, memorize the multiplication tables, memorize the chemical elements. but not really learning science, not really learning how to learn. And I think that's what, Pierre, your work is really focusing on, is how do we get students to really understand science and use science in their everyday lives as they're students and then as they grow up to be older. So I think it's been a really great evening to hear about that, and I'm just very impressed with the work you've done and the diversity that you've brought to it.